Greetings to you. Welcome to Physics with Ben. Don't forget to like my videos, subscribe, and share to those that need it. In today's video, we want to look at a brand new topic, electric field 1. And so we want to look at the following items. We want to know what a field is, types of field, types of force fields, electric field, point charge and a test charge, what they all mean. Electric field lines or line of force for a point charge and a test charge. Electric force between point charges, that is Coulombs Law. Electric field intensity, and then electric potential. So let's begin without wasting much time. Let's start with item number 1. What do you mean by a field? Don't forget to subscribe and share all these videos to those that need it. This topic is one of the topics that keep coming in WIAC, and it will interest you to know that all the videos I make here are videos concerning topics that always come up in your external exams. What do you mean by a field? A field is defined as a region or a space around which the influence of some physical agents such as magnetic force, electric force, and gravitational force of attraction can be felt or experienced by an object placed in it. We want to look at item number 2. There are types of fields. There are two main types of fields in physics. We have the scalar fields and the vector fields. Examples of scalar fields are heat energy or temperature. What do we mean by scalar fields? Scalar fields are those fields that has only magnitude but no specified direction. For instance, if you sit close to the fire, if you sit here, you'll be warmed by the fire. If you sit this side, you'll be warmed by the fire. If you sit up, you'll be warmed by the fire. There's no specified direction with which the heat that is coming out from that fire will reach you. Even if you sit down, you still feel the heat from the fire. So for this, we say that temperature or heat energy is a perfect example of a scalar field. How about vector field? So we say that we have scalar fields, and then we have vector fields. For scalar fields, we say we have heat energy, and then or temperature. So how about vector fields? Just as you know what we mean by vector quantities in physics, vectors are those quantities that have both magnitude and specified direction. So when we're talking about a vector field, we mean that a field that has both magnitude and also a specified direction. Examples of vector fields are gravitational field, magnetic field, and electric field. So we are done with item number 1, 2, and we are now at item number 3. So we are going to look at what we mean by we're looking at item number 3, types of force field. Item number 3, types of force field. There are, just as I said, types of vector fields. Don't be confused. These are different ways the questions will keep coming in your exam to confuse you. When we're talking about types of force field, we simply mean all the examples of vector fields. So the force field we have here are gravitational field, electric field, and magnetic field. So for the sake of this class, we are looking at electric field. So you know how we come about this topic right now. Electric field is a vector field that has both magnitude and also a specified direction. Electric field is also an example of what? A force field. That is why I started this lesson from point number 1 down to point number 3. So what do we mean by electric field? You may write. Electric field is simply a region or a space around which the influence of electrostatic force of attraction or repulsion can be felt or experienced by a charge placed in it. We are done with the definition for electric field. We want to look at point charge and a test charge. What do you mean by a point charge and a test charge? In physics, I keep telling guys that some topics are related. For instance, let me say this one. A point charge is simply a charge that has a positive or a negative charge. A point charge has a positive or a negative charge. And sometimes in an electric field, this point charge, the charges are not known until they are brought in the electric field. The behavior of the test charge will now tell which type of point charge we are dealing with. Do you get it? So I can say that a point charge is simply a positive or a negative charge brought into an electric field. As simple as that. So what do we mean? And a point charge is denoted with a capital Q. A capital Q. If it's a negative one, the negative sign will be placed there. And if it's a positive one, you're going to have a positive sign placed there. What do you mean by a test charge? What do you mean by a test charge? We have looked at the point charge as having a plus or a negative sign. A test charge is simply a very small, sensitive, positive charge that is brought into an electric field to detect and show the direction of the electric field. A test charge is a very small, sensitive, positive charge that is brought into an electric field to show and to detect and show the direction of the electric field. And the direction of the electric field is always from positive to negative charge. So a test charge again is also used in electric field to detect the presence and the type of the point charge that is brought in the field. So a test charge in electric field behaves like the compass needle in magnetic field. You know, with the help of the compass needle in the magnetic field, you'll be able to know which type of the poles that are involved in the magnets. Either it's a north pole or a south pole. You may bring in a magnet that has no leveling. You know what I'm saying? But immediately you bring that magnet close to the compass needle, the compass needle's deflection will tell you if that magnet is having a north pole or a south pole. So the same way the compass needle behaves in magnetic field, that is the same way the test charge behaves in electric field. I believe we are through with this right now. We want to look at electric field lines of force. Electric field lines of force. If I place a positive charge here, and then I place another negative, this is a plus positive charge, and then a negative. So this is a plus point charge, and then a negative point charge. The direction of electric field will be like this. Now, I said that a test charge is used in detecting the direction of electric field. So if I bring in a test charge in this field, it will travel in a direction tangential to this curve. It will travel to a direction tangential to this curve. So what we mean here is that the direction of this electric field is from left to right. So we call this electric line of force. This is exactly how it behaves. It points from plus to negative sign. So you may be faced with some questions to detect the direction of electric field for a plus point charge, for a negative point charge, or for 2 points charge, negative, negative, or plus, plus, plus together. How do you go about it? Very simple. Let's call this diagram number 1. Let's look at diagram number 2. Let's suppose that this is a plus point charge. The direction of electric field for a plus point charge will be like this. The field lines will be drawn straight like this. Good. So the direction for this field. Now we said that in electricity, plus plus is gonna be repulsion, negative negative gonna be repulsion, and plus negative is gonna be what? Attraction. Now let's suppose that there is a small point charge, test charge in this field. A small positive test charge placed in this field. Because of the presence of this small test charge, there's going to be a force of repulsion here. And so the field will be directed outward. The field for a plus charge will be directed in the outward direction. How about a negative charge? If I draw a negative charge here, the direction of the electric field will point inward. For a negative charge, let's assume that it's a small test charge here. Let's assume. So the direction for the field lines will be in, will point in. Because there's going to be a force of attraction. So the lines will point in. This is that for that. For a plus charge or a negative charge. Now let's look at what happens when we bring in plus and negative charge together. When you bring in plus and negative sign charges together, this is what you're going to have. You're going to have something like this. This is plus charge and this is a negative charge. So the field lines will move from here to here. From here to here. The arrows will point in this direction. The arrows will point in this direction. So the arrows will move up here and come in here. The arrows will move down and then enter here. This is so, in between this, there's an electrostatic force of attraction that is in between the two of them. So this is what happens for plus and negative point charges. Let's look at what happens when we bring in negative, 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 and plus, plus. For negative, don't forget what I'm looking at here is electric feed lines. Electric feed lines. For negative, this is what you have. It's going to be a force of repulsion. It's going to be a force of repulsion in between. So this charge will move this way, something like this. And so the direction of field will point in, as I said earlier. It will point in. The direction of field will point in. That is for a negative pointer. So in between here there is electrostatic force of repulsion pushing the charges to move apart from each other. That is what happened for negative negative. For plus plus, this is what you have. For plus plus, you see how something like this, but this time the arrows are pointed outward. The arrows are pointed in the outward direction. The arrows are pointed out. Instead of in, the arrows are pointed out. Please take notes. The arrows will be reversed in the other direction. This is happening because of the presence of the test charge in the electric field. The arrows will be pointed outward. So this is for plus plus charges. You will be asked in your WIEC or your GCE that two charges W and X are placed and the field lines are like this. Detect the types of charges that were placed in the field. So when you see something like this simply means the two charges are what? Plus plus. That will be your answer. So we are through with electric field lines of force for a point charge and a negative charge. We want to quickly look at the next subtopic, Coulombs Law. So we are through with this. We want to look at Coulombs Law. So write electric force between points charges, brackets, coulombs law. There was a guy called Coulomb. Don't forget, there's another video for this topic. There's another video on electricity. For this is on current electricity. This one is static electricity. So he studied static electricity and he discovered that there was a relationship between the electrostatic force of attraction and the charges, and also the distance of separation between them. If you understand the gravitational field very well, this topic, you have no challenge in this topic. And what I'm trying to say is that if you understand Newton's law of universal gravitation very well, then you have no challenge in this topic. So let's write. In this topic, you'll be asked to state Coulomb's law. So how do we state Coulomb's law? So let's write. Coulomb's law states that the electrostatic force of attraction or repulsion between 2 point charges Q1 and Q2 is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. So what Coulomb is saying, that Charles Coulomb is saying, is that this is Q and this is this could be Q1 and this could be what? Q2. Not minding what the charges are, be it a plus plus or negative negative, there is always a force of attraction or repulsion between the 2 point charges. And this force from here to here, this is the vector force, and from here to here is the distance of separation between the forces. And this distance is simply the square of the distance apart. So what we are saying is that the force of attraction or repulsion is directly proportional to the product of these charges Q1 and what? Q2. And this same force is inversely proportional to the square of the distance between these charges. So this is a direct proportion and this is an inverse proportion. It means that if the distance between the two charges decreases, the force of attraction or repulsion will increase. If the distance between the two charges decreases, the force of attraction or repulsion will increase. Here it means that if the quantity of the charges increase, the force of attraction between the two charges or the force of repulsion will also increase. So combining these two variations together, we're going to have what is called a joint variation by saying that F is inversely proportional to Q1, Q2, and then, F is directly proportional to Q1, Q2, and inversely proportional to what? The distance between them. Removing the sign of proportionality, this sign, we're going to write that our F is equals to K, Q1, Q2 divided by what? D squared. Is that all? That is not all. What is the value for K? K is a constant of proportionality given to be 1 all over what? 4 pi absolute naught. That is the value for K. And the numeric value for K, is given as K is equal to what? 9.0 times 10 raised to the power 9. Now, what is the SI unit for K? From here, if you write that your K, Q1, Q2 is equal to F D squared. And you divide both sides by Q1, Q2. Q1, Q2. This will go and your K is equal to what? F D squared over Q1, Q2. Dimensionally, F is measured in units of Newton, D is in meters, and that is meters squared. And then Q is measured in the unit of Coulomb. So Coulomb times Coulomb will be what? Coulomb squared. So the SI for K is given to be what? Newton meter squared per Coulomb squared. So this is 9.9 times 10 raised to power 9 Newton meter squared per Coulomb squared. That is the value for K. That is the unit and the numeric value for K. We are not going to stop there. We are still moving on. And so there are three ways of writing this equation. You may write this equation this way. You can call this equation number 1. Or you may choose to write this equation this way. That your F is equals to Q1, Q2 divided by what? 4 pi absolute naught D squared. Equation number 2. You can choose to write this equation like this or like this. I believe this is well understood. So we want to look at, so this is Coulombs law. So from here it means that increase in D squared because F is to decrease, 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 increase, increase, decrease, increase, increase, decrease, decrease. That is the meaning of the equation. We want to quickly look at, we are done with Coulombs law. We want to quickly look at electric field intensity. Electric field intensity, electric field intensity. The electric field intensity E is defined as a ratio of the electrostatic force of attraction or repulsion to the charge Q, and it's measured in the units. You know, force is also a vector, so it's measured in the units of Newton per Coulomb. That is the equation for the electric field intensity. I want to consult it quickly. Yes. The electric field intensity is defined as a force over charge, and that is that for that. So the force of attraction is also defined as electric field times charge. You can call this your equation number 3 and your equation number 4. That is that for that. And if you move on, if we have a charge, good. So this is A and B, and here is your R. So that is how we represent it. So here we call your BQ, and here is your point charge. So quickly from this equation, we can still generate an equation for the electric field. We can still generate an equation for the electric field. We know that the electrostatic force of attraction, F, is given as what? It's given as KQ1, Q2 all over D squared. Good. Now, let's write. Let Q1 be equals to BQ and Q2 be equals to what? Small q. So if we do that, we are going to say that the electric force of attraction or repulsion is given to what? K capital Q small q all over D squared. We want to bring this into this place. And if you do that correctly, this is what you are going to have. For here, we know that our electric field as a vector quantity is given to what? This force, which is here right now, as K Q small q divided by what? D squared. All divided by what? This Q. If you do that correctly, you know that your electric field is defined as K capital Q small q divided by D squared times 1 all over Q. This Q will cancel out this Q. And so your E, electric field, is defined as what? K capital Q all over D squared. And you know that the value for the K is 1 all over 4 pi absolute naught. So you are free to write that your electric field is defined as capital Q divided by 4 pi absolute naught D squared. So you can call this your equation 4. You can call this your equation number 5. Equation number 5. I believe this settles it. What does it I call the physics of cut and join and substitution? These are the equations, the things we do to get advanced equations. So let's quickly look at electric potential. The electric potential, I'll write here, the electric potential, bracket V is simply defined as a ratio. The electric potential V is simply defined as a ratio of what? As a ratio of work done, all over charge. The electric potential V is defined as a ratio of work done all over charge. The electric potential also has an equation related with electric field intensity, as from E is equals to V all over D in the units of. So what we are trying to say here is that electric field also has an equation as E is equals to what? V all over D in the unit of what? Volts per meter. So this equation 3 is for electric field. Equation 5 is for electric field. You can call this equation 6 is also for electric field. So electric potential is given as this all over this. And from this particular equation, we can cross multiply and say that our electric potential is also here is given as V is equal to what? E times D. Using the fields of cut and join, we are free to bring the whole of this, equation number 5, into this equation. So we can say that this is equation number 7, and this is equation number what? 8. So electric potential also means V is equal to what? Capital Q divided by 4 pi absolute naught d squared times d. This d will cancel out one of the d here. So V is given to what? Q all over 4 pi absolute naught d. You can call this equation number 9. Yes, to this we have come to the end of today's video. In the next time we meet, we are going to use all of these equations to solve a good number of questions. Thank you, God bless you. Share this video. Bye-bye.